In this lecture, we'll discuss wet scrubbers. We've been talking about primary particulate removal. That is the removal of primary particulates generated in a unit operation, an incinerator, a mechanical process, some operation such as that. We've spoken about wall devices. That is, those devices that remove a particulates at the wall. These include gravity settlers, centrifugal separators, and electrostatic precipitators. We've now been speaking about dividing devices. That is, those devices that divide the flow into much smaller flow. This includes filtration and wet scrubbers. Wet scrubbers divide the flow by sending it through many small droplets of water, and it's often combined with a cyclone. As shown here, we have dirty gas entering a scrubber device. So gas is combined with liquid. See the liquid here. And we're trying to transfer the particulates from the gas phase into the aqueous phase. So now we have a mixed gas and liquid, both of which are dirty now. They, in this case, flow into a cyclone separator. So what we're doing is we're separating the gas from the liquid so that we have clean gas. And now the problem that we have is dirty liquid. So the particulates have been moved into from the gas into the liquid. So we have a mass transfer process here. And now we need to separate the particulates from the water. So we would have some collected solid and clean liquid, which then we can recycle back into the system. Now remember, most cases our gases are warm or hot, so we will have evaporative losses. So we need to, in many cases, add makeup water in order to replenish that supply of water and replace that which has evaporated. The problem with this device is that it changes the problem from an air problem to a water pollution problem. And we need to make sure that we're cleaning that water sufficiently and collecting those solids in a form that they can either be disposed of or reused. So with wet scrubbers, the primary aim is to remove particles that are typically between about 0.1 to 20 microns in size. We need to ensure that we have adequate dispersion of the liquid, and so that we have good contact between the particulates and the liquids, and we can achieve mass transfer of those particulates from the gas phase to the liquid phase. Shown here is a typical type of system. So you can see the boiler produces flue gas, and that flue gas contains SO2, so sulfur dioxide. In this case, what we have is a wet scrubber. Quicklime or calcium oxide has been added. That calcium oxide reacts with water to form calcium hydroxide, shown here, and the SO2 reacts with water to form H2SO3 acid. And that acid can react with the calcium hydroxide to form calcium sulfide, which then is collected in the collection tank. So we've not only removed particulates, but we've also removed SO2 And we've neutralized that SO2 so that the gas is not corrosive. Now, in order to remove these particles, we need, as I mentioned, we need good contact and we need good mass transfer. So these particulates, and we'll draw here's a particulate. These particulates can come in contact with the water droplets by a number of means. First is initial impaction. So we have water droplets here. And with inertial impaction, as you saw in the filtration lecture, the gases move, they're moving with the flow stream, but the flow stream moves, they're unable to maintain the ability to remain with that flow stream, and as a result, they kind of speed off the track and come in contact with the water droplet. Interception, we have a particle, it's moving with the flow stream, and it intercepts with the droplet. And then diffusion, as you recall, occurred with these really small particles, and they can diffuse and contact the particulates. In all cases, we need mass transfer, we need an electrostatic attraction that keeps the particles attached or with the droplets. Now, there are a number of types of wet scrubbers that we can use. The most simplest is the spray chamber. And here the air passes through a chamber with the liquid spray produced by some sort of spray nozzles. And you can see that in both of the figures here. In figure A, what you see is we have the dirty gas flowing upwards. We have clean water, flowing downward. So we have a counter current flow, and we end up with clean gas out the top of the unit, and we end up with particulate-laden or dirty water from the bottom. So this is a counter current flow system. We can also have what is referred to as a cross flow system. Now we have dirty gas entering from the side. We have our spray nozzles spraying liquid down. So our gas is flowing perpendicular to the liquid, and our clean gas flows out the side, and the dirty water on the bottom. Okay, and notice in this case too, we have a entrainment or a mist eliminator. So what we're doing is we want to remove those droplets of water so that the gas is not only clean, but it is also dry. Now we need to maintain sufficient gas flow so that the liquid droplets are suspended for a sufficient period of time that we get good contact, that we get good mass transfer of those particulates into the droplet. Otherwise, the liquid just settles to the bottom, and we end up with clean liquid and dirty gas. Again, in this situation, you will need to replace the water, so you'll need to add makeup water to replenish the water that evaporates. Spray chamber scrubbers are useful for particulates that are 8 or so, 10 microns in size. You can achieve greater than 90% efficiency there. And for particles that are greater than 25 microns, you can achieve approximately 99% efficiency. Cone spray nozzles tend to be the most effective. Pressure drops are quite reasonable, typically about 1 to 4 inches of water. The smaller the particles that you're trying to remove, the larger the delta P, the larger the pressure drop. So the smaller the particles, the larger the pressure drop. And these can be used, for instance, in paper dust control, so in paper towel manufacturing, in fiberglass production, so for instance with latex aerosol control. Again, that water will need to be treated before it is recycled. And baffles can be added in order to improve gas-liquid contact. We can improve the efficiency as compared to the spray chamber units by introducing the flow tangentially. So what we're doing here is we're using the cyclone separator, and operates exactly as we've spoken before. So the dirty gas enters tangentially. That causes the gas to spiral. Now what we do here is we insert banks of nozzles in a ring fashion inside the conventional dry cyclone. So we're spraying clean water and towards the outer edges of the cyclone separator. This improves the contact between the dust or the particulates and the liquid droplets and improves mass transfer. If it improves mass transfer, it improves efficiency. It also promotes droplet separation and produces smaller droplets of water. Again, that improves mass transfer. So here we can achieve efficiencies of approximately 99% for particles size 50 to 100 microns and between 90 and 98% for particles between the sizes of 5 and 50 microns. I'll give you just a sense here. Pressure drops are a little bit higher than we saw with the spray chambers. Again, because you have better mass transfer efficiency, which means better removal of particulates. Now, the sieve plate separator is again a little more complicated. So what we have is we have a series of plates, and you can see the openings in those plates. And again, we have the dirty gas entering. We have the clean liquid from the top. But here what we're doing is we're introducing the liquid, and what happens is that liquid will collect on the top of these sieves. That causes a foaming of the liquid water mixture, improves the gas liquid contact, improves the mass transfer of the particulates into the liquid. The disadvantage is you've got a higher pressure drop. Now, just want to step aside a little bit here. We're talking about particulate removal, but one of the aspects, and you saw it in that first image with the boiler, is that we can remove both particulates and gases with these units. It's the only unit we've spoken about that can achieve both particulate removal and gas removal. So when we talk about absorption of gases, you'll see that the same units that we're talking about can also be used for absorption of gases into a liquid phase. The design equations are very different, but the units are identical. We can also use venturi scrubbers. Now here what we're doing is we have a venturi, so we have a significant pressure differential. Our dirty gas enters, and our clean liquid also enters at the head of that venturi. The gases flow through the throat of the venturi. That creates very small bubbles. So if we have very small bubbles, very small droplets of water, again, that improves mass transfer. The disadvantage is the pressure drop. So we'll have much larger pressure drops with a venturi scrubber than we will have with the other units that we've discussed. However, the efficiency is greater. These are still simple to use. They're easy to install, easy to maintain, so you can actually even take a conventional cyclone separator and add a venturi injector to that where you're adding your liquid and your gas. And here's just another unit showing a cyclone separator with a venturi injector. We'll look at the removal of venturi scrubbers from a design perspective. We simply don't have time to look at the removal for all of these different processes. However, this will give you a sense of the various parameters that affect removal efficiency. Now, efficiencies are highly variable, and we can improve efficiencies, for example, if we increase the gas velocity, that will increase the efficiency. If we increase the contact, which is quantified with the parameter R, which is equal to the liquid gas flow rate divided by the gas flow rate. If we increase that, then we will increase our efficiency. So if we increase R, we'll increase efficiency. Particle diameter will also play an important role. As the particle diameter increases, the efficiency decreases. As the density, on the other hand, of the particulate increases, the efficiency increases. As we mentioned, mass transfer is extremely important. So as we increase the diameter of the droplets of liquid, the efficiency will decrease. And then as we increase temperature, that will increase the viscosity, which will decrease the efficiency. So we can represent this mathematically using the equations given here. So phi is referred to as the inertial impact parameter. And it is equal to the Cunningham factor. Now the Cunningham correction factor is used because very small particles do not obey Stokes' law, and this, if you look at it, is based on Stokes' law. So these very small particles tend to slip between the gas molecules. That reduces the coefficient of drag, so we need this correction factor. And this is equal to 1 plus 6.21 times 10 to the minus 4 temperature in degrees Kelvin divided by the particle size in microns. So just make sure you're using the correct units when you're using this equation here. Now, we then use the inertial impact parameter to determine the efficiency, which is equal to 1 minus e to the minus k, where k is a correlation coefficient dependent on the unit itself. R is the ratio of the liquid gas flow rate to the gas flow rate, and we've defined the inertial impact factor. If you look at this equation, this is using the mixed flow model. This figure here shows the complexity of the relationship between particle size and droplet size. What you see from this figure here is there's really an optimal droplet size that is needed to remove particles of a given size. Now, recognize this is a hypothetical situation. All conditions would be the same. So we have the same gas flow rate, the same liquid flow rate, same venturi scrubber, same temperature. But you see that, as I mentioned, that there's this complex relationship and there really is an optimal droplet size. So what I'd like to do is go through an example where we have a venturi. Now this is a venturi scrubber. So we have 10 micron size particles. These particles have a density of 700 kilograms per cubic meter, and you're given the operating parameters of the venturi. So it has a throat area of 1 square meter. We have a gas flow rate of 94.4 meters cubed per second. The gas has a temperature of 150 degrees C. We have a liquid flow rate of 0.13 meters cubed per second. We have a correlation coefficient of 200 meters cubed of gas per meter cubed of liquid, and we have a droplet diameter of 100 microns. So I've copied the information from the previous slide here so that we can walk through this set of calculations. So remembering, we need to determine the Cunningham correlation factor to account for the slip of these particles between the gas molecules. So we'll do that first. So we have C is equal to 1 plus 6.21 times 10 to the minus 4 times T in degree Kelvin divided by the droplet diameter in microns. Again, make sure your units are correct. And substituting, we have 1 plus 6.21 times 10 to the minus 4 times 423 Kelvin divided by the diameter of the particle, which is 10 microns. And that is equal to 1.026. So it's roughly about a 2.6% change that we'll see. We need to determine the gas velocity at the throat. So that gas velocity is equal to our gas flow rate divided by the area of the throat, and that is 94.4 meters cubed per second divided by 1.0 meters squared, and that is 94.4 meters per second. The viscosity at 150 degrees C is 25.2 times 10 to the minus 6 Pascal seconds. So you want the viscosity in Pascal seconds. And the inertial impact parameter is C, so it's the 1.026 times the density of the particles times the gas velocity, which we just calculated, times the diameter of your particles squared. Make sure this is in meters. And we'll divide that by 18 times the diameter of the droplets, which is 100 microns. Again, make sure that is in meters, times the viscosity. And our units cancel, and we have a inertial impaction parameter of 146. The efficiency is then 1 minus e to the minus k times r times the square root of the inertial impact factor, and that is equal to 1 minus exponent of minus 200 times the ratio of our liquid gas, so that's 0.13 meters cubed per second, divided by our gas flow rate, which is 94.4 meters cubed per second, times the square root of 146, and that is equal to 0.964. So we have 96.4% removal of these 10 micron sized particles. Lastly, let's look at the advantages and disadvantages of wet scrubbers. One of the major advantages of a wet scrubber is that you can safely treat flammable or explosive dust. One of the major problems of baghouse filters and electrostatic precipitators is the potential for fires or explosions as a result of this dust. However, in this case, what we're doing is we're transferring that gas or contacting it with a liquid, and that significantly reduces the potential for fires or explosion. As I've mentioned, unlike the other processes that we've discussed so far, wet scrubbers allow for both gas absorption and dust collection in the same unit. Wet scrubbers handle mist. They also cool hot gases, which can be beneficial, especially with certain types of subsequent processes. So for instance, if this followed a baghouse filter, for example, there's less potential of explosion or fires because of the temperature decrease. It is variable collection efficiency. It can be operated under different conditions, so we can change, for instance, our water droplet size or our liquid flow rate. And one of the major advantages is that it can neutralize corrosive gases and dust. So we can add other chemicals. For example, you saw in the earlier slide the addition of quicklime, calcium oxide, to neutralize the SO2. Major disadvantage is the potential for corrosion. Significant problem is the formation of corrosive liquids, and that often will mean that we need specialized materials in order to minimize the corrosion, or we need to add chemicals in order to neutralize the corrosive chemicals. We end up with contaminated effluent water. So we've transferred the problem from a gas phase to a liquid phase, and now we need to treat that liquid phase. In colder environments, freezing can be a problem. We've got these very small droplets of water. Potentially these can freeze, and that causes problems. Another problem is that you may wish to recycle the collected particles, but now your collected particles are in an aqueous phase, got a high water content, even if you remove much of that water, and it may make it much more difficult to recycle these collected particles. And as a result of the transfer of the problem from a gas phase to a liquid phase, then we can often end up with expensive disposal of the sludge, which often will have quite a high water content. Lastly, what I'd like to do is look at how do we choose a collector. So now we're looking at all of the unit ops that we considered or that we've studied for particulate removal. So for small or occasional flows, we may wish to use a throwaway device. So for an example of this is the filter that is in a cigarette. It's not reused, simply thrown away with the cigarette. Or an air filter in the car, or the filter on a furnace. The particulates remain in the unit. There's no need to process those particulates, and they simply just get thrown away with the device. It can also be used as a final cleanup device. For example, a HEPA filter can be used as a final cleaning device for air flowing into a microchip clean room. For large and steady flows, you're looking at collection devices that operate continuously. Okay. So here the collected materials are collected. They're removed either continuously or intermittently, and those particulates that are removed can be potentially reused, or they can be discarded. For sticky particles, we may wish to use a throwaway device. So, for instance, removal of tar. The tar tends to stick to the materials, and because of that, if our flows are small or occasional, it makes sense to use a throwaway device. If our flows are large and continuous, but we have a sticky particle, then we're likely to want to remove it into a liquid. So we're looking at wet scrubbers or wet electrostatic precipitators. We also may want to make sure that the surface is either coated with the flowing liquid or is treated with a non-stick material. Again, with these, if we're using a wet scrubber or a wet ESP, we have a liquid stream that we must now treat. Now for particles that agglomerate to each other, these are very easy to remove. And you may even be able to use a gravity settler, because if the particles are large enough, they can easily be removed with a gravity settler or perhaps a centrifugal separator. For particles that stick to surfaces, we get back to that sticky particles. we're really looking at special surfaces. So these can be Teflon coated surfaces or Teflon coated fibers in the case of a filtration device. So we want, in order to minimize the adherence of that particle to the surface. Electrostatic charge, extremely important in ESPs. We mentioned this when we talked about ESPs, and even in terms of how when in the 1990s, when we switched from high sulfur coal to low sulfur coal, that fly ash had a different resistivity, and the removal with the ESPs actually decreased. These electrostatic charge also impacts how well these particles adhere and stick to the fibers on a filter, or how well they stick to each other. So electrostatic charge can play a significant role. It can both aid or hinder the collection of particles. For large, non-sticky particles greater than about 5 microns, the cyclone separator is the unit that you will most likely use. For particles that are less than 5 microns, you can use electrostatic precipitators, filters, or scrubbers. So you've got a much wider range of unit ops that you can choose from. For large flow, pumping becomes a major expense, and that makes what scrubbers generally very expensive, and you most likely will choose another device. So it typically, as I said, makes wet scrubbers expensive and eliminates those from the choice of units. And then for corrosive gases, you need to consider the material selection, and you may need to add chemicals in order to neutralize the acids or bases. So from this lecture, you should have a better understanding of scrubbers and also have a better understanding of how we choose a unit and to remove primary particulates.